Hey everyone. So a couple of days back, Dr. Yann LeCun announced on his social media that the V-Jepa 2 paper is out. And since then, a lot of people have been talking about it in social media and other fronts. So that made me thinking, okay, can I use AI tools at my disposal, and can I try to understand as much as V-Jepa 2 as possible? Because when I looked at the paper, it was like a 30 plus paper, so page paper. And so I just wanted to see if I can use AI tools. So as always, I'm going to use Saral AI and NotebookLM to decode this paper. So let's jump right in. So first I'm going to use Saral. So the website is saral.democratizedresearch.in. And once you log in, you can click on the PDF, and then I'm going to upload this PDF here. And I'm just uploading this V-Jepa 2 paper. It's a large paper, as you can see. It's about like 35 megabyte. And then I'm going to click on one click to poster, right? And then I'm going to just say PDF. So the poster is going to like just quickly summarize the paper in just a single page. So let's just wait for that to happen. Meanwhile, this is the paper V-Jepa 2.1, Unlocking Dense Features in Video Self-Supervised Learning. So this is from FAIR and University the Zaragoza. So it said, we present V-Jepa 2.1, a family of self-supervised models that learns dense, high-quality representations for visual scenes in both images and videos while retaining the strong global scene understanding, right? So, and a little some more is there. It uses a dense predictive loss and a deep self-supervision and multimodal tokenizer. So these are the ones that are in bold. So not yet read the paper, so I'm hoping that the AI is going to kind of help me understand the paper in a simpler way. So the poster is done. It took less than 30 seconds, so that's nice to see. So I've already downloaded a version of this, so let's go and read that paper, read the post here. So this is what it generated. You can see that V-Jepa 2.1, unlocking dense features in video self-supervised understanding. So it is able to get all the authors mostly from here. And let me zoom in a little bit. It says V-Jepa 2.1 is a family of self-supervised models designed to bridge the gap between global scene understanding and high-quality dense spatio-temporal feature representation. By introducing a dense predictive loss and hierarchical deep self-supervision, the model learns features that are spatially structured, semantically coherent, and temporally consistent across both images and videos. The resulting architecture achieves state-of-the-art results on diverse benchmarks ranging from monocular depth estimation in robotic navigation to fine-grained action classification. So some more information is here. So when you go to, this is just the abstract, and then it says that learning representations that simultaneously preserve dense spatiotemporal structure. So that is very important when you have videos, the spatiotemporal structure for localization and capture complex dynamics for global recognitions, remaining significant challenge in computer vision. While previous JEPA models, which is like JEPA stands for Joint Embedding Predictive Architectures, excelled at global motion modeling, they lacked the fine-grained local spatial information required for dense tasks. Right, so and V-Jepa 2.1 addresses these by forcing the model to ground every token in a specific location through an expanded predictive objective applied to both masked and visual regions. Then it says that the architecture utilizes a dense predictive loss that applies self-supervision to both masked and visual context tokens to prevent visible tokens from acting as non-spatial global aggregators. So deep self-supervision is implemented by applying the predictive loss hierarchically. So like in a way that it happens step by step, iteratively using different scales or some other layers across multiple intermediate encoding layers to ensure strong training signals are propagated throughout the entire network. This system incorporates a multimodal tokenizer. That's very interesting, with modality-specific patch embeddings and learning tokens to enable a unified, efficient training on Vision Mix 163 million dataset with temporal duplication. So I'm going to stop here mostly. I do get some idea about it. I would not say I have the exact idea of what it is. So, but let's, now that we have done, when you've gone through this in a very quick way, let's also next do the podcast. The podcast I'm hoping was going to kind of like make it clear what the paper is about. So I'm back in Saral AI, and I've already uploaded the PDF. So here you have this one-click podcast. So I'm going to click on this, and then I'm going to choose English and generate podcast, right? Let's wait for it to happen and come back once it's done. So it's still generating. It says about 18% complete. It says less than 2 minutes. It usually takes under 2 minutes. So let's just wait for that to happen. The podcast is now done, so I'm going to click on play. So what I'm going to do is I'm going to play the audio here, and I'm going to also try to correlate that with the paper in another tab. So let's see how that goes.
Rohan, ready to dive into this V-Jepa 2.1 paper? It looks dense. V-Jepa, what does it even stand for?
Joint Embedding Predictive Architecture. Basically, it's a way for computers to understand images and videos.
Okay, joint embedding makes sense. So, what's new in version 2.1?
The big thing is how it learns dense features. Think of it like really detailed vision.
Dense features like seeing every pixel clearly.
Close. It's about understanding the relationships between all the parts of an image or video, not just the big stuff.
Ah, so not just there's a cat, but the cat's paw is on the rug.
Exactly. And V-Jepa 2.1 is much better at this than previous versions.
How did they achieve that? The paper mentions a dense predictive loss.
That's key. They made the model predict what's missing in the image, but also learn from what's there.
So, not just focusing on the masked part?
Exactly. Before, they only penalize the model for errors in the masked areas. Now, the whole image contributes to the learning.
Interesting. It's like learning the content.
So okay, now I'm able to understand a little bit. Again, not gone through this paper, but masked attention is one of the ways in which self-supervision and also large language models and others are all trained, wherein like parts of you have a data and then parts of it are masked and then you're learned. So what the podcast is telling, it seems that usually the masking is the way to do it. And here, they're not just relying on the masking part, but they're also relying on what is already there in the image, and then they're using that information also in some way. What exactly the way is, which still has to be seen, but at least that's what I understand from listening so far.
Text, not just filling in the blanks.
Precisely. They also used deep self-supervision. What do you think that means?
Maybe learning at different levels of detail within the model itself?
Spot on. Applying the learning objective at multiple layers, not just the final output.
Makes sense. Like teaching a student step by step instead of just giving them the final exam?
A good analogy. And they used multimodal tokenizers to handle images and videos together.
So, one model to rule them all, image and video?
Pretty much. It allows for more efficient and unified training.
Okay, so dense predictive loss, deep self-supervision, multimodal tokenizers, anything else?
Scaling. They made the model bigger and use more data. Always helps, right?
Haha. Usually, what kind of data are we talking about?
They used a
This is the vision mix, 163 million. Well, these are the places where AI gets a little, it's not able to pronounce that fully, but still is doing a good job.
What are the concrete improvements?
state-of-the-art results on a bunch of tasks, object interaction, anticipation.
That sounds complex.
It is. Predicting what objects will interact and when. Think robots understanding human actions.
Oh, and action anticipation too, right?
Yeah, like predicting what someone will do next in a kitchen scene from Epic Kitchens.
Impressive. What about robotics? The paper mentioned grasping?
Huge improvement there. 20% increase in grasping success rate on real robots.
That's amazing. So, better vision leads to better manipulation?
Exactly. And they also saw improvements in robot navigation and even depth estimation.
Depth estimation, so the robot can see how far away things are?
Precisely. It's all about building a better world model for the robot.
Okay, I'm starting to see the bigger picture. This isn't just about pretty pictures.
No, it's about enabling robots to understand and interact with the world more effectively.
So, V-Jepa 2.1, a step towards more intelligent and capable robots?
I think so. It unlocks richer visual understanding, which is crucial for all sorts of AI applications.
This is really exciting, Rohan. Thanks for breaking it down.
My pleasure, Aisha. It's amazing what's happening in self-supervised learning.
So that was helpful. I wouldn't say I got everything, but at least I understand that this tries to have a self-supervised model for both image as well as video, and tries to, from what the podcast is describing, tries to also incorporate very minute details in both the image and the video in such a way that, say, the robots and other for other activities, the the world model in terms of vision, in both of image and the video, could be like understood. That's what I get from here. So let's move on and see what more I could understand from using more AI tools here. So far, I used Saral AI's poster and podcast tool to kind of feature to kind of understand what the V-Jepa 2.1 paper is about. I definitely could understand a little bit more than before. So now I'm going to use NotebookLM and try to see what more it can tell me about the paper. So let's go like that. So to save on time, I have already like uploaded the PDF and created the NotebookLM. So you can see that this is a chat, V-Jepa 2.1 unlocking dense spatio-temporal features in video SSL. So there is a lot of other artifacts here, audio, video overview, and so on. So right now I just used the video overview and slide deck. Usually you also used to use the audio, but maybe for now I'll just use these two and figure out. So let me first start with the slide deck, right? So let's me click on slideshow and let's see what it has. So it's amazing to see what type of how very nice slides it has done, right? So it says from blur to high definition structure, V-Jepa 2.1, unlocking dense features in video self-supervised learning. And I'm just going to read out and try to understand in my head, try to talk to myself how this is. The missing link in multimodal world models. Current embodied AI models face a strict trade-off. They either understand the precise spatial layout of a single frame or the overreaching semantic action of a video. Real-world physical reasoning requires both. So like what it's trying to say is that the visual language models just using a single frame, they're really good. And maybe action model, which has taken time, and video language models, they're also okay. But there is not a good mix between the vision language models and video language models together. And real world physical reasoning requires both, right? And I myself have faced this. I've seen, like, I've done a lot of benchmarking using like RealLens as well as video language models, and I've seen how these two are very different. So there is a graph here, feature fidelity, and in the x-axis is the modality. So you have image only to unified image plus video, right? So this is be like image only kind of thing, and then this is all the like the image and video. So it says here that the previous V-Jepa 2 tried to mostly feature on the video part and tried to get a very good temporal understanding, and the local representation is not very good there. And whereas Dino V3, like I mentioned, this is the visual language like model when you do the grounding and other things. So they are really good in understanding single image, but it does not work very well on the videos. So you can see that this is mostly the image part. And what they really want, and both of these are from Meta and then previously Dr. Yann LeCun's leading efforts. So what they want is convergence of all of this. Basically the convergence of both as very good spatial high fidelity like what Dino V3 would give, as well as temporal understanding as what V-Jepa 2 would give, right? This is really nice to see that in the first slide itself, it's laying out what the paper is really trying to talk about. So then it says the cost of lazy global aggregators. So it says when self-supervised prediction losses are applied only to masked regions. So I think this is what the podcast was also trying to say. The visible context patches have no incentive to encode local geometry. So basically, like, it'll try to find out the missing patches, the masks, but there was no incentive to like say what the local geometry, like, okay, if there's a car missing here, maybe what is happening in the tree, and is there a road, and then things like that. They default to lazy global aggregation, resulting in latent representations that cannot localize fine-grained structures or track precise object boundaries. So this is an interesting part, right? So this is the V-Jepa 2 feature map, and it's just a fragmented spatial structure. So I don't fully understand this part, but I'll just let this go for now. Whereas here it says that V-Jepa 2.1 feature map tries to kind of get this car semantically coherent boundaries. So you can say that just from this heat map or mask, like I can say that there is some car here, right? Although I'm not able to feel it, and that's what V-Jepa 2.1 is doing. The same car should have been here, but for some reason it did not show up. So my guess is that this is the same, I don't know which car it's trying to represent from this image. Is it representing this car? If it is, I'm wondering why the front and the back seem like reversed, like in the sense that left, right. It should have been, the back should have been facing this side, but anyways, that's what it tries to kind of do. So it says processing modalities in their native form. So previous models insufficiently duplicated still images to mimic 16-frame static videos. So what they were trying to do is that instead of trying to model it as a video which has spatial and temporal information, it was just trying to mimic like 16-frame static videos in which like you have each frame was an image, right? So V-Jepa 2.1 introduces a multimodal tokenizer, details 2D and 3D convolution extract native features, while learnable modality embeddings allow a single shared encoder to disentangle static appearance from dynamic temporal motion. So this is what they're trying to say. This is from a static image, they get the 2D convolution output, and then from the multi-frame video, and they do a 3D convolution using, like, say, 3D patches, and you get a 3D output, and they would kind of maybe mix both of this, either, I don't know, maybe concatenation or some other way, and they get a modality embeddings, and this is what kind of forms this unified vision transformer block, right? So that's at least gives a good high-level picture of the whole thing. The context loss engines enforces local continuity by applying a distance-weighted L1 loss to visible context tokens. V-Jepa 2.1 forces every patch to ground itself in its exact spatio-temporal location. Tokens closest to the masks are penalized most heavily, enforcing strict local spatial continuity across the entire scene. So here it's assuming that they are having a video, so it's going to be like, is what I'm understanding from this. So the old way was that you have these masked and, need not necessarily be a video. The old way was, if these were the masked patches, right? The penalization was only between the mask patch here to mask patch here, mask patch here to mask patch here, and so on, something like that. So by applying a distance-weighted L1 loss to context visual token, V-Jepa forces every patch to ground itself in its exact spatio-temporal location. So what they're trying to do here is that tokens closest to the mask are penalized most heavily, ensuring strict local spatial continuity. So from the arrows here, what it seems is that here, there is no arrow between this and this, right? So it says tokens closest to the mark are penalized. So whereas here you have, there's an arrow between here and here, then here and here, and so on. Lambda I is equal to lambda times distance minimum of I, is what is given here. So I think like tokens closest to the masks are penalized most heavily. So you can see, maybe it assumes that when this patch is closer to this patch or the masks patch, so these would be penalized more in comparison to this is the distance, like in comparison to, say, maybe this and this, or this and this and so on. That's what I'm trying to understand from this, right? Balancing dense precision with global comprehension, forcing dense representations initially degrades the global action recognition. Deep self-supervision applying the laws hierarchically to immediate encoder layers rescues global performance. Combined with 163 million scaled diverse outputs, the architecture achieves a rare dual state-of-the-art. Wonder what that means. So maybe it's getting state-of-the-art in more than 2 specific problems or solutions, right? So they're saying that this is the baseline. The baseline for dense tasks. Well, ADE2K is a very standard data set, and for scene understanding and so on. So you can see that baseline is 22%, whereas for the global, okay, this is the baseline. For the green is the dense tasks and the blue is the global tasks, right? So with context loss, the dense increases from 22 to like 33. And then the metric here is mean IOU, intersection over union. So this is, I don't think it's the accuracy here. Whereas they also have accuracy here. Okay, accuracy is also put here. So it's IOU on this axis and accuracy on this axis. This is a nice way of presenting information. So it's like actually like three variables are presented here. So then you have this one also increases, deep self-supervision also increases. So previously you can see that 75%, then it increased to like, well, yeah, 70, 75, 60, 65, 60, 70, 80. So there is something seems to be wrong. I don't know. I'm getting confused with how the labeling is done here. So I'm guessing this is either, I'm not sure if this is from the paper or is it from NotebookLM, which probably did the wrong generation, right? Anyways, it seems that things are better when you go with what the paper is proposing. So it says translating latent resolution into physical action. Global features know what an object is. So it may identify a cup using a mounting box. Object detectors are really good, but fail to precisely judge its exact physical boundaries in 3D space. So if you want to know in 3D, you need like molecular depth estimation, and you need to know depth, basically where it is. The high definition dense features of V-Jepa 2.1 allow medical model predictive control algorithms to plan longer rollouts without latent space collapsing, yielding a 20% improvement in zero-shot physical space. So this is really good. So it's able to see, you can see that it's able to grasp it very nicely here. And that's what they're trying to like show. High-speed planning in the latent space, training conditional diffusion models directly inside that high-dimensional embedding is unstable. So because V-Jepa 2.1 representations are intrinsically structured and stable, latent trajectory planning requires only 8 denoising steps, delivering a 10x speed up in robotic navigation over precise architecture without scaling, sacrificing accuracy. So this is a start, and this is the goal. Like in when you have like reinforcement load, robotic implementation, reinforcement kind of thing, right? And it says that the standard architecture has 128 denoising step, whereas V-Jepa 2.1 tries to like decrease it to just 8 denoising steps, giving a 10x speed up. So it just says redefining the state of the art in molecular depth. So here it's like, I think Dino V3 also had a molecular depth estimation, and here it seems to be much better than previous Dino V3. And then it says anticipating fine-grained future interactions. This is more in terms of they're getting one more good result, new state of the art or EVO 4D benchmark. This is, I think, robotic action or navigation kind of data sets. And then it says the foundation for physical world modeling. So they say that this is going to be a great for physical world modeling, incorporating like image, video, and depth, and so on. So you have dense perception, which involves depth estimation and semantic segmentation, global dynamics, action recognition of what is happening, and video question answering, as well as embodied action, zero-shot robotic grasping, and faster navigation. So this is the last slide. So this is really nice, very detailed. Hoping it's accurate and it's actually like, well, I definitely got a really good understanding, better understanding progressively as before, right? So that's really nice to see. So let's see further on how we'll just do a video also and then see if that helps in the overall a very good understanding of the paper. So let's just get that. So I'm back in NotebookLM, and this has generated a 7-minute video for the V-Jepa 2.1 paper. So let me make it full screen and let's see what it says. So one thing I was wondering here is that why is it showing 2 images here? So it should have just showed 1 image. It seems to be a replication. The second thing I'm now able to understand is that these are the embedding visualizations of V-Jepa 2.1, if I'm not wrong. I mean, not 2.0 if I'm not wrong, and this is going to be for 2.1. And this is able to get the cat and the person and all of that very clearly is what they're trying to say. It's almost similar now. Now I'm getting better and better understanding. It's like similar to the grad cam visualizations, which used to like highlight areas of the image of the convolution layers and so on. But it's similar, not the same here. It's just that this is another visualization, and they're showing that V-Jepa 2.1 does a very nice visualization. So this is really nice, right? So this is the third time we're listening to the same information, but look what AI is doing here. And I've not yet read the paper, and I'm pretty sure when I glanced through the paper, all of this information was present just in text. I don't think they had a very nice visual or illustration or something like that, right? First, we heard the same thing from the podcast. It was saying that, it said that they're not just masking it, but they're also taking into account both the masked patches as well as what is already there. And then next we saw how the NotebookLM slide, that showed a different visual, but maybe using the graphs and with distances and things like that. Now, the same NotebookLM, it's presenting the same visual and illustration in a completely different way. And when we kind of try to see this, imagine you're in the class and you're trying to see this, grasping this information in different ways, I'm able to actually understand things better now, right? So that's the power, true power of AI in what's happening today. I mean, of course, assuming all of this information is right and there is no hallucination and so on, but appears so that so far it appears there is not much. So that's good. Just continue. Really, the way the illustration is done, I don't think these were parts of the original paper. I wonder how they got. I mean, I wonder why you have these, the coffee and things like that. But this shows as time varies how this whole thing happens, right? And what is the predict the next object and in the video and so on. So that's really interesting, right? So you could, if it gives multiple answers, you can have like how you give the results for retrieval based systems, as in instead of giving just one single answer, you would give the answer based on the say top 5 answers or top 10K answers and so on. And you can say that, you know, this answer was part of the top 5. In that way, like it could really like boost. Well, I mean, on one hand, you'll also know one of the answers is possibly there. And on the other hand, this will also boost the overall metric, which is used to measure the accuracy and precision. Well, I didn't really get there. It says mean absolute precision is what I'm understanding. I'm not sure why I'm not sure why this was just 5.67, which is, and then when this changed to 7.71, statistically, what does this represent, right? Yes, I'm NotebookLM is saying it's a substantial improvement. In my head, I'm still not sure why is a 2% 2-point improvement really substantial, unless it tries to like substantiate over it. Maybe it is, but I'm not understanding from this particular slide at least. Yeah. So this one is a better way of telling it, right? Okay, 20% in terms of how a robot would do the action, right? But the previous one I didn't really understand. That was really cool. Yeah. So that brings us to the end of this video on understanding V-Jepa 2.1 just using AI tools. About an hour back, I had totally no idea what this paper was about, but just using some AI tools like Saral AI and NotebookLM, I have some idea of what it could be. And this could help me to say if I want to read the paper in more detail or maybe use more AI to understand the paper as a deep dive. That will help me in definitely like understanding it further. So with that, we'll check and see the next video. Bye.